Okay, very simple situation here. I took a ball and I tossed it. So it almost, but not quite reached the ceiling, fell to the floor. Okay. Asked everybody to estimate where the ball was when I released it, where the ball was when it reached its maximum height. And if you're watching this, you can use some sort of stop action with your video to get some idea how long it took to get from here back to here. That would be useful information if you could time that. But based on estimates that people made, we get various equations of motion. And the task was find the equation of motion, because that's really kind of the central thing that you're looking for. Now, the equation of motion is the equation for position. X of t equals what? Just like the equation for theta of t for the rotating beam that we're going to continue to look at quite a bit. So x of t equals what? Well, first of all, you know that x minus x naught equals v naught t plus 1/2 at squared. And this x is x of t, but we generally write it without the t because it's implicit that this is a function of t. Okay, so now you made estimates of x naught, which would implicitly be, for most of you, you would almost certainly let x naught be the height from which I released it. Okay. You don't know v naught, you know. What else do you know? Well, you know x naught, that's not going to be totally helpful. You know a, because this thing is falling freely. You have the acceleration of gravity. Okay. We have to determine what v naught was. If we know what v naught is, you know what a is, you know what x naught is, we've got our equation. Okay. So how are we going to get that? Well, the five kinematic quantities, okay, or uniformly accelerated motion. And since the net force on this ball is gravitational force, it is uniform. Mass of the ball isn't changing. It follows that it has uniform acceleration. Now, right now, we haven't talked about mass and force and everything, but that's what it comes down to. And that's the reason we say that this ball has a uniform acceleration in the vertical direction. Okay, and we'll see more about that later. There's a little bit of air resistance, so you know that this is only a very good approximation. We're assuming uniform acceleration. So what can you determine? Well, okay, here's the path of the ball. It goes up, it comes down. Okay, here's x naught. Okay. At this point, v is 0. Well, we can analyze motion from here to here. Okay. We know initial position. We know how far it is. Okay, so position here is x max. motion from release to maximum height. X minus X naught equals X max, which we estimated, so we know this. We know X minus X naught. B equals 0, B being VF. And you want to use VF for that. I tend to want to do that too, but the way your text often sets things up, they don't put the F in that. Okay. And it's perfectly valid to call that VF as long as you know that that is V of T at the time that you get to the top. Okay. And what else do we know? Acceleration is negative G in whatever units. So if we want to use feet per second squared, well, it's negative 32 feet per second squared. Very close to that, because especially here where it's enough altitude that 9.81 really becomes a 9.8. Probably. It's real close. And it depends a lot on the geology and everything. So we're safe using 9.8. Actually, I like to use 10 because it's really easy to calculate with, and then you can always subtract 2%. It's easy to do. Makes very convenient calculations. It's the kind of thing even engineers do. Okay, just a convenient back of the envelope calculation that you can then verify with your software and everything. Okay, so anyhow, there we have it. So we know this, we know this. And that allows us to solve for V naught. Okay. Now, what do we do if we know these three things? Well, it doesn't hurt to have our equations written down. We should be able to write those equations down pretty much instantly. Our equation. Okay. It takes a while to develop an instinct about what equation to use here. So it's very useful to just have the equations written down and see, let's see, what equation contains these three quantities. Okay, let's see, this will got X minus X naught, it's got V, doesn't have A, it doesn't have T. So we can't use this equation. Go with the simplest equation, this one, but again, we don't know A, and we actually do know A. So we know A, and we know V naught, but we don't know V naught, do we? So we're kind of stuck with one of these equations. They're quadratic equations in one thing or another. So that can be a complication. Let's see. If we go to this equation, we know X minus X naught. We know A, but we don't know T. And we have some hope for this one. Well, yeah, we know A, we know X minus X naught, and we know V. We can find D naught. Okay. This is the only equation that appears to lead us to any conclusion. So we circle this equation, we take these three quantities and throw them into this equation. And out of that, we get V naught equals plus or minus square root of I would want to get a negative sign someplace. Something's not clicking in my head when I write this thing down. today, so, we get v squared minus two a times x minus x naught. We know all these quantities. So we get our V naught. Now that we know V naught, what else don't we know? We don't know T. I would go to this equation or this equation, either one of which gives us an easy solution for T. Okay. So we take this along with everything else that we know, and we plug it into this equation. And out of that equation, we get T. V minus V naught over A. I would do the algebra before I substitute quantities, okay? Although a lot of times there is something to be said for thinking in terms of the quantities. So what I'm typically seeing on your papers is a lot of equations with a lot of stuff substituted in. And then a lot of confusing steps that would be a lot simpler if they were done algebraically with symbols, okay? And I'm just afraid that could be a little bit confusing, even though, I mean, if all you're doing is solving the equations without thinking about the quantities, I'd do the algebra. Okay, I'd advise you to do the algebra. Anyhow, from that, you get this and this, and now we can take this V naught, put it here. And we know A, just put a check mark next to A. And we know X naught. And now you've got an equation. And the equation works if T equals whatever this is. You will get your X minus X naught, distance from here to there. Okay, but this is the general equation. It works for any T. Because the acceleration doesn't change, the initial velocity was what it was, and X naught was what it was. So now you have an equation you can use to answer the questions I'm going to ask you next. Okay, so using your equation, because your equation is going to depend on your estimates. What was the ball 6 feet above the floor? What was the ball at the position of release? What was the velocity at each time it was at the position of release? Because it's at the position of release twice. That's When and where was the speed 2 meters per second? When did the ball hit the floor? And at what speed? This single equation, you can answer every one of those questions fairly easily if you know how to set up the equation. And if you don't, you'll learn something. Some of the questions are a little harder than others, so see what you can do. Okay, in perspective, the reason I'm doing this is that first place it reinforces the homework that's due today. Okay, and vertical motion, which you need, because now what we want to do is we want to take this ball, watch carefully. Okay. I'm going to toss the ball out this way. Okay. Now, how high did it rise? Okay. You can make your own estimate. How far did it travel this way as it rose to the top? Okay. Then there are all kinds of questions I can ask about the motion. We superimpose the vertical motion, which is the same as if I tossed the ball up to whatever that maximum height was. Okay. Just toss the ball vertically up to this height and it falls. The motion is exactly the same in the vertical direction. We're going to call that the y direction. We've been using that, but it's actually going to be y. Okay. So if you do the same analysis you did for this one, just using this height and the height here, okay, you're going to get an equation of motion, but it's going to be a y minus y naught. All these here goes up an angle height and right down to the floor. You can estimate from the y-axis, you can estimate this height, which might be y naught. You can estimate this height, like y max. You could then get the entire equation of motion for the y. As soon as you got y naught and y max, you do the same thing we did here when we called it x. Okay, you know how far it went, that's your y minus y naught. Okay, you know its velocity here was 0, so vy is 0. So you say vy equals 0 here. Ay is negative g. And from here to here, displacement to y minus y naught is y max minus y naught, whatever you estimate. If you estimate it's half a meter high here, then this would be half a meter, and you can solve the equations exactly as we did here. Okay. You're going to get y minus y naught equals e naught y t plus 1/2 ay t squared. Okay. Now, if you estimate how far it went in the horizontal direction, So we put our x-axis anywhere we want to, and okay, here. So we've got an x naught, and we've got an x here. This is x of t when it's at its maximum height. Now, what is t at the maximum height? Something you can determine from your y values. Okay. Get t from your y of t. Now that you know the time it takes to go from here to here, you can figure out the average velocity. Okay. Vx average don't want to use maps for this time, so I'm going to call this time t. This is how far it goes in the x direction. And this is how long it took. T1 is the time from here to here. Okay. So the x motion acceleration is 0. There's no force in this direction. If you neglect air resistance, and you pretty much neglect it for that ball moving at that speed. So the acceleration is 0. V naught x is Vx bar. And if you know x and x naught and all that stuff, you know Vx bar. Okay. So that so the 1/2 ax t squared is 0 because ax is 0. So we have V0 f t. That's your x equation of motion. This, of course, is x of t. The situation is actually pretty simple. So I guess I'll illustrate it. Got about 11 minutes, it will take long. Okay, for some simple approximations. Okay, let's assume this much. Y naught is 0, the thing leaves my hand. That's where we start. And x naught is 0. So there's our 0 point. Y max is 1 meter, so it goes up a meter. Further than it did when I tossed it on screen, but you wouldn't have been able to see it. I didn't toss it up a meter. Okay, so Y max is a meter. X is 2 meters at the maximum height. And the picture is simply, here's Y, here's X, here's Y naught, here's Y max, and here's your path. X is 2 meters here. Okay. Now, if you use equations of motion, and I'll let you work out how. Okay. But then Y max will occur in about 0.43 seconds. Vy of 0 is about 0.4 meters per second, or about 4 meters per second. Actually be about 4.5 meters per second, but I'm just throwing ballpark there. Okay. At 4.4. If this is 0.43 seconds, it'll be about 4.2 seconds. 4.4 meters per second. So using 1/2 A is 4.9 meters per second squared. It's 1/2 G, right? So there's your equation. Y of t equals this. Since Y naught equals 0, you throw that away. Now, if you want to measure everything from the floor down here, which is maybe, 1.7 meters below this, if you want to measure everything from the floor, and that might be convenient, that's fine. You just let Y naught equal 1.7 meters. Okay? That makes sense? You just choose where your 0 point is. It's arbitrary. And there are good reasons, especially if you want to figure out when it hits the floor, to let Y equal 0 at the floor. But if we're analyzing just the motion from here to here, then it makes sense to let Y equal 0 here. Okay. Of course, this picture doesn't depict Y naught equals 0. If you want to depict Y naught equals 0, we're going to start it. If X naught, Y naught equals 0, we'll start it here. We'll have this, and the floor will be in negative position. You can work that out. We'll see examples and stuff. The overview isn't just as simple. Now, there's some things that get kind of complicated. There's some situations that are mathematically complicated. Okay. So you have to worry about that to some extent. x of t is just v zero x t. How do you get v zero x? It's 0.2 meters over 4.3 seconds, 1.3 seconds, which is approximately 4.6 meters per second, question mark. Now, another thing you're going to see, is to give you something to be excited about. Okay. At the initial point, there's something wrong with this. No, there's nothing. Okay. Your initial y velocity about 4 meters per second. Initial x velocity is a little bigger than that. Ballpark, you can work out the numbers. Okay. So what is v zero? But here is v zero. What's the angle? It's the arctangent of the y coordinate over the x coordinate of the velocity. And you can work that out with your calculator very easily. Okay. Now, if I give you the initial velocity, let's say I throw it a little hard. You know it is, let's say, 7 meters per second. If that equals 37 degrees. At 37 degrees might be about there. And this is 7 meters per second. What's the path going to look like? It's going to continue going in the x direction with its initial velocity in the x direction. Well, okay, you just do a little trigonometry, you find the x and y components of this vector. They're 5.6 meters per second in the x direction, 4.2 meters per second in the y direction. Well, now you can find the equation of motion in the x direction and the equation of motion in the y direction. But there's your equation of motion for y. B naught y, well, I got it there in numbers. Okay. AY is negative acceleration of gravity. X of t minus x naught is just B naught x. Oh, wait a minute. Well, there's the symbols. Use my numbers for instance. It's this. And then you can substitute V naught x, which is 5.6 meters per second squared, and 4.2 meters per second, not per second squared, 5.6 meters per second, 4.2 meters per second here. And we got a question. Okay, write down things before I write them down. I was already thinking about the 1/2 a2 squared. I have to put a 1/2 here, which is really a 1/2 error. Okay, so got to be careful. Okay. The point is, if you know the initial velocity and the direction and the initial position, you got your equations of motion. You can totally solve the motion. This is all you need to answer any question you want about the motion. Okay. Now that's the mathematical framework, the logical framework. The assignment you have, the first assignment in chapter 3, which I think might not be due until Wednesday night. I think it's due on the 20th. So we'll talk about it a little more, but you really want to master chapter 2 and read chapter 3. Even start on that homework. If you do the homework at the last minute, you learn way less than you do if you spend the equal amount of time over 2 or 3 days. It just doesn't sink in. Things don't make sense. You're panicking at the end. Now, maybe not. Maybe you totally understand it. Some people are pretty smart. Okay. Everybody's smart enough. You got to do the work, but everybody's smart enough. You can see that. Okay. But you got to spend the time and spend it as intelligently as possible, which is not at the last minute. And if you haven't been able to get some of these assignments done, I don't know if they're available for review. I kind of think they are in some way. Review them, look at the videos. There's some good stuff there. And read the text, and also you ought to read through the problems at the end of the chapter or at the end of the section in some cases. Okay. You don't have time to solve them all, but read through them and say, okay, here's what I do for this one. Here's what I do for that one. I don't have a clue about that one. We'll look at it in a couple of days. Okay. How am I going to formulate this problem? How am I going to understand intuitively what's going on with this problem? Intuitively, you have uniform acceleration up and down. You have constant velocity this way. That's projectile motion. It can get tricky though. It can get challenging. There's one case, and it's the case we most want to do in the lab. When we roll the ball off the end of the ramp's at an angle, we want to find out how long it really takes to fall. Okay, but all we know is how far it went before it hit in the X direction and the Y direction before it hit the floor. That one is hairy. You're going to love it. Okay, and we'll kind of develop the mechanics to do that as you work through chapter 3. It's, I think, the hardest question you can be asked from chapter 3. Okay.